And our next speaker is Matthias Hanauske. And we will make it like this, that at least the speaker will also show the camera, that we see who is speaking. And Matthias, now the floor is yours.
Okay, thanks a lot for the invitation to give the talk here. Can you see my presentation? I think yes. Or...
Yeah, it's fine.
Yeah, okay. So today I will talk about the gravitational wave signatures of a Hadron-Quark phase transition in a binary compact star merger. Before I will come to the Hadron-Quark phase transition, I will say a little bit about the relativity codes we have and what equation we solve and how the so-called hypermassive neutron star looks in the interior. And afterwards, I will come to the Hadron-Quark phase transition. So in the computer codes, we solve the Einstein equation together with the hydrodynamical equations using a so-called 3+1 decomposition of space-time. You can see it here. We decompose the whole four-dimensional manifold into spatial hypersurfaces. And two important functions are there, the alpha, which is here in the 3+1 decomposition, and the beta, which is a kind of frame dragging. So we solved that on the computer, and when we now look what comes out of the simulation, there are in principle three kinds of outcomes. The first outcome we saw in the first gravitational wave, which we observed with LIGO, where we had a total mass of the system which was in the intermediate range. And after the merger, a so-called hypermassive neutron star was created, which lives roughly for 1 second and then collapses to a black hole and produces then the observed gamma ray burst. And this is what we saw in the first gravitational wave. We also saw a second gravitational wave, which was in the total mass much higher. And the simulation also shows that one gets with such a high mass a prompt collapse to a black hole, where not so much material is emitted. And we are looking forward to get the third possibility here, where we have a total mass of the system which is not so high, where we can have at the end a so-called supramassive neutron star, which rotates fast and comes then to a stable, highly rotating neutron star. So here we see the simulation. Here we see the gravitational wave, and here we see the density. After the merger, which was here, a kind of wild post-merger phase enters, where you have here a kind of double core structure. And as time goes on, so after 10 milliseconds here, the double core structure dissolves, and the maximum value of the density is then in the center and increases, and then finally gets so high that the hypermassive neutron star needs to collapse to a black hole, which we see now here. This is the Wingdown phase then. So one can divide the different stages into the inspiral phase. This is what we saw in the gravitational wave emission. And then we see a kind of wild post-merger phase, which then goes into one can explain it with these dances then. You can maybe look in this paper, but the main thing is the following, that we get the inspiral phase, a wild post-merger phase, and then a quite of quasi-stable phase, and then the collapse to a black hole. We see this also more clearer when we look at this power spectral density of the emitted gravitational waves. So within the first roughly 5 milliseconds in this wild post-merger phase, we get several different frequency here. But then after some time, only one, the F2 frequency remains, and this is a supramassive simulation where we do not see a collapse to a black hole. By looking at two different ones of the same total mass, it depends a lot on the equation of state where this F2 peak lies, which you see here. Now I will come a little bit more and explain what is going inside such a hypermassive neutron star, and there we transform in a so-called co-rotating frame. Here you see again the spectral the spectrogram of the emitted gravitational wave with here the instantaneous gravitational wave frequency, and we would take now the star. We sit on the system, on the star, and rotate with the star. And this is a so-called co-rotating frame. Here, you see a little movie of such a co-rotating frame. Here you have the temperature plotted, and usually the two neutron stars rotate around, but we are sitting on the system now and looking how, how the temperature and how the density looks like then. Additionally, we put some tracer particles here to follow what the fluid cells are doing. Here you see now a simulation of a totally hadronic equation of state, the so-called LS220 equation of state. Here you see the density, and here you see the temperature. Okay. So this is right after merger now. You see that after some times there are some vortices here, and you see that exactly there the temperature increases, and we then get after 10 milliseconds a kind of not so hot interior, but a hot ring-like structure. And this is now on the equatorial plane. In the co-rotating frame. So we look now at the same simulation, but plot here the temperature and here the density. We are now here, and the colors here represent the fluid cells of the hypermassive neutron star, and the color indicates where inside this is so dark, and this color here means that it's in the interior, so at a radius about 0, 1, 2, and this is more outward here. So we look at the same simulation, and here we see this wild post-merger phase, and the tracer particles, what they are doing. Here you see that the interior gets denser and denser, but the interior is not so hot, yeah. But here you see this hot temperature ring, what we saw, which happened roughly about 1 to 2 times normal nuclear matter density. And yeah, so as I said, this is with the LS220 equation of state, but we see such a structure also with all the other purely hadronic equation state like DD2 or something like that. to understand that, why such a temperature hotspot and ring-like structure comes, we have to understand how the star, the hypermassive neutron star, is differentially rotating. So here you have the angular velocity omega in the 3+1 decomposition. So it depends on this alpha. The main part is here the phi component of the velocity of the cells, but we need to subtract some kind of frame dragging because of the the rotation. The whole space-time rotates with the star. Okay, now here we plot the temperature again. Here we plot the omega, but now not in a corotating frame. And we see exactly more or less the same for the temperature and omega. Here you have the temperature hotspots. Here you have the omega maxima. And the temperature is high exactly there where the high positions of the omega turns over to the low omega. So where you have, and you see here also when the temperature wing-like structure occurs, then later you see this also in the omega. So it means now that the star is in the center, not so highly rotating, and it has a highly rotating ring, and this we see also in the temperature, not so hot interior, but a ring-like structure. Oh, I have to. We see this kind of differential rotation with a slow rotating inner core and this omega maximum in all of the other equational states. So here, maybe I can skip that. So now we come, what's going to happen when we take an equational state with a Hadron-Quark phase transition. And so our main question is now, can we detect the Hadron-Quark phase transition, the quark-gluon plasma, with gravitational waves? And here are a summary of some papers, but the main outcome is, yes, we can detect the Hadron-Quark phase transition with gravitational waves, and I think it will be possible probably in the next 5 to 10 years. First, I will explain this article here, which was the first simulation of a hybrid star merger with a temperature-dependent equation of state having a Hadron-Quark phase transition. We have here now again the temperature versus density. At the here at the background, you have the quark fraction. Yeah, you see here in this model, you get a quite sharp a deconfinement transition about 3.5 times normal nuclear matter, and you see here more crossover. So I turn on the video and we look now what's going to happen after the merger. So now we are at merger, so this is the wild post-merger phase. You see that at some regions here, at the hot regions, which are not so dense, you get a kind of a little quark fraction. Yeah, you see here the temperature hotspots moving around, and in the interior of the temperature hotspots you have that. But now, more importantly, the density in the interior gets higher and higher, and now comes really here to the phase transition in the interior. And when it enters that, you will see it heats up now, and in this model, unfortunately, it collapses to a black hole. And this is the last simulation snapshot what we have before it collapses to a black hole. And here we have logarithmic density now. So again, just before merger, we get an increase of temperature in the interior when it enters the Hadron-Quark phase transition. This looks like that. And then just right before collapse, it looks like that. You can also plot this plot, not temperature versus density, but temperature versus a chemical potential. And then it looks like that. It looks like, yeah, a kind of bird here, where you have here the neck and here the head. And the head is composed of totally deconfined matter. Okay. Yeah. The gravitational waves emitted are here, and you see a kind of a different ring down here when it collapses to a black hole. When you take a total mass which is not so high, like here, you see a kind of also phase shift of the gravitational waves. Here we have no phase transition, and here we have with a phase transition. And this phase shift is due to the high temperature hotspots, which have a little bit of quark fracture. Okay, now we come to the second possibility, which is called the delayed phase transition, because this was a phase transition triggered collapse. Because when the phase transition happens in the simulation, what I showed you, it immediately collapses to a black hole. But there are also other possibilities where we see where the signatures of the Hadron-Quark phase transition are much clearer. This is now the following. We have here, these lines over there are the simulations where we have no phase transition. Here we have included a phase transition, and the phase transition in both cases it begins at a little bit more than 2 times normal nuclear matter density, and the mixed phase region ends here at a little bit above 4 times normal nuclear matter density. You see here that, and the 2 curves are just a little bit of difference in the total mass. We are focusing now on the red curve. You see here that it follows, here's the maximum density plotted, and here the time. So here is merger, and in the post-merger phase, then here, it gets denser and denser, and when the phase transition is going to happen, it collapses here to a much, a hybrid star. And this oscillates around and gives the kind of hybrid star remnant. We have used the following equation of state, which is done here. So this was the equation of state without a phase transition. And here we have included at, as I said, roughly 2 times normal nuclear matter density, a sharp Gibbs-like phase transition. And we have here a little bit a twin star shape. So here's an unstable region. Yeah. And here it goes over like this. Additionally to this cold equation of state, we have included in thermal ideal fluid component for the neutron star merger simulation. And what we saw here is when it enters the phase transition, it oscillates here around. This is the interior, and yeah, so we are focusing now here on the situation where we are just right before collapsing. You see here the density and temperature. We have here a little bit double core structure as you see, and now and we are here just right before entering the phase transition. Yeah, and now the thing collapses. Yeah, which is the next plot over here. It collapses, and we are now here, and you see here we have the region in the interior which is totally of deconfined matter, and here we have a kind of mixed phase region, and we have a kind of unsymmetry which came because before the collapse there was a kind of unsymmetry in the system, and when it collapses it creates such a shape here.
5 minutes, Matthias.
Yes, okay. So here is for example also this point, and also this point now here, and this is a later point, and now I will come to one thing what is in the temperature structure difference, because we see here different regions of high temperature. These outer regions here, these are due to the rotation profile. But this inner region here is due to the Hadron-Quark phase transition, and it lies exactly here in the mixed phase region. I want to show this for a little bit later time. Here we have the density, here we have the temperature, here we have the omega, and here we have the frame dragging. And this is in the equatorial plane, and this in the XZ plane. You see here that here in the XZ plane, it's maybe good seen, that inside the mixed phase region, you get here a kind of hot temperature region, but which is not due to the rotation profile, which is here. Yeah, so it looks then like this. So the main thing is how we can detect such a phase transition. This is a really good thing. The simulation, what I showed you is this here. Here we have the emitted gravitational waves without a phase transition. And here we have the emitted gravitational waves with a phase transition. Yeah. So at the beginning, they are the same, but when they are going to enter this this collapse to a smaller hybrid star, the star speeds up, and as a result, the gravitational wave frequency gets also higher. If we look at the simulation with a little bit higher mass, we see the same, but here we see that it collapses to the hybrid star, giving a higher frequency here, but then it collapses to a black hole here. One important thing, what we saw also is, because here in the gravitational wave, we plot the 2-2 component of the emitted gravitational waves, but because of the unsymmetry, we also see in the H1-2 component, only in the case where we have a phase transition, an increase here, and this is due to this unsymmetry after collapse, which you see here. It now is the collapse, and due to this wobbling around, it creates this H1-2. So about the prompt phase transition, I think Andreas Bauswald will talk, and about I did not have time to talk about the signatures within the in spiral phase, but there, when one, for example, would have a twin star structure, there are also good signatures for us to detect the Hadron-Quark phase transition. Yeah, so this is my last slide. I also did not talk about this maybe third gravitational waves from a neutron star black hole binary, but I think personally it was a black hole system. And in the future, we will have probably the Einstein telescope or the Cosmic Explorer, and Kagra will also enter, LIGO India will enter, and I'm really looking forward to the 041. Thanks a lot.
Okay, thanks, Matthias. So this was a talk which really concerned our topic, namely the phase diagram. You showed the phase diagram and how in the phase diagram a merger evolves. So very nice. My question immediately before I see raised hands, where do you see the maximum mass of, so this divide between stable neutron stars and black holes? And in your equation of state, I think you showed one curve of maximum mass. So what is the maximum mass of the neutron star in your equation of state?
Yeah, so I in principle showed mainly two simulations. In all of the simulations, the maximum mass was in a range about 2.1 solar masses, the maximum mass. The difference was in the really temperature-dependent equation of state where we get the phase transition triggered collapse. When it came to the maximum mass, it gets unstable, yeah, and as we result, it collapses to a black hole. So within this model, no stable hybrid stars are possible. In the other model, I showed the equation of state was this little twin star shape, and the maximum mass was at much higher densities, and these were really hybrid stars having a huge deconfined quark core.
So you don't believe that neutron stars without rotation can be as heavy as 2.5, 2.6?
Yeah. So I said that I personally think that this was a black hole merger, but I found it interesting. So if it was, if the maximum mass is really higher than the proposed value by Rezzolla and others, then I think probably dark matter could be important, and this will shift the maximum mass, and as a result, it would also solve the hadron puzzle. Yeah. So, but I'm not the expert there. Yeah, but it could be possible. But yeah.
I have seen several dark matter predictions which lower also the maximum mass, but that's another.
But there are also some with higher.
Yes. Okay. I don't see raised hands. So if anybody wants to have a short question now, please speak up. Otherwise, we leave the discussion for the discussion session. And we thank Matthias once more.